Dear friends, welcome to my video lecture series. In our today's topic, we are going to discuss the power method. What is power method? So, what we can do using power method, that is what we are going to discuss in this video lecture. So, using power method, we can find numerically largest eigenvalue. Got that? Numerically largest eigenvalue. Okay, what is numerically largest eigenvalue? Suppose I am having -5 and 4. Which will be numerically largest. We don't bother about sign. That's what the meaning for numerically largest. -5 will be the numerically largest one. So this is what the concept they are mentioning with this sentence. Right. Now come to the part. So using power method, we can find numerically largest eigenvalue of the given square matrix. Right. So already you studied in your first semester itself how to find the eigenvalues and eigenvectors. That and all I had done analytically with some other methods. But here you are going to deal with numerical way. Particularly, power method is the iteration method. Iterative process already you have used in some other methods also, like Newton adoption, uh, regular falsy, and iteration method. There are several iterative methods are there, and here power method is also one among them. Right. So when we can say eigenvalue is the dominant one. Suppose if I'm having lambda 1, lambda 2, etc., lambda n with the distinct eigenvalues of a, then lambda 1 greater than lambda 2, etc. So lambda 1 will be the dominant eigenvalue here, modular value we have represented. So we are not going to bother about negative sign here. Right. Now, this concept it will take place for MCQ. That's why I'm covering that part also. This method is applicable only if the eigenvectors v1, v2, etc., vn are linearly independent. You know how to, when we can say a vector is linearly dependent and independent, so we can check like that. So it should be linearly independent. And it may be true for what will be if the eigenvalues are not distinct. That means what? Repeated. For that case also, even it may be true. Right. Now we'll tell you how to find the smallest eigenvalue. Smallest eigenvalue will help you to find all the eigenvalue of the given matrix. They may ask in the big question. So smallest eigenvalue of A, the dominant eigenvalue of A, we are going to use power method to do that. But now we are going to find smallest eigenvalue of A. What are the steps involved? First, to find the dominant eigenvalue of A using the power method concept, iterative process. Right. Next, compute the matrix. We have to form a new matrix B with this concept. A is the given matrix minus lambda 1 just before we found using A. So it will be A minus lambda 1 into I. Using that, we have to form a new matrix. Now, we have to find the dominant eigenvalue for B, the newly formed matrix. Then finally, the smallest eigenvalue of A will be the dominant eigenvalue of B. What you are going to find in the previous step, that plus lambda 1. Already we found lambda 1 is nothing but dominant eigenvalue of A. If you are adding both, you can find a second eigenvalue. So if you know the second eigenvalue, we can apply this property lambda 1 plus lambda 2 plus lambda 3 is equivalent to sum of the main diagonal elements trace of A, trace of the matrix A. This concept you can use. Clear? So using this, you can find the third eigenvalue also. Right. Now, I have given one problem. Using this example, I would like to explain the concept of power method. Find numerically largest eigenvalue of A and the corresponding eigenvector. One eigenvalue, I mean, it should be numerically largest and corresponding eigenvector they asked to find. Right. Come to the point. Power method iterations, as I told you already, it's an iterative process. So initially we are going to assume one eigenvector, I mean column vector x1 equivalent to 1 0 0. So you can ask, sir, whether it is necessary to assume like this only. No, we can assume this as 0 1 0, or it may be 0 0 1 also. It won't be wrong. Clear? Whatever it may be, the assumption you can make here. It should be eigenvector should be non-zero column vector. You know already when you're defining the concept, Ax equivalent to lambda x. Here lambda is the eigenvalue and x should be the non-zero column vector, eigenvector. It should be non-zero. That's why at least any one of the element you can take as 1. Clear? So here particularly uh, uh, we assumed x1 equivalent to 1, 0, 0. If you are interested, you can assume 0, 1, 0 or 0, 0, 1 also. No issues here. Now I'm going to multiply the matrix A with the x1. A into x1. So A, I have taken the given matrix. I'm going to multiply this. You know how to do the matrix multiplication, row with the column wise. What will be the multiplication? It will be 25 plus 0 plus 0. Next multiplication 1 plus 0 plus 0. Next row 2 plus 0 plus 0. So the result will be what? 25, 1, 2. And the important thing is here try to take numerically largest value from this as common. Whatever the numerical. Why I am using that word numerically largest? Important thing is numerically largest value you have to take. That means what? Suppose in my matrix I am having 25 is here. Minus 30 I am having. Another value 1 is 2. So numerically largest I have to take. Which I will take? This one minus 30 you have to take. Numerically largest. So here numerically largest is 25. Take that as common. If you're taking that as common, then it will be, which will be 25 into 1, 1 by 25 and 2 by 25. We can use calculator to do that. You get this fraction values. That's it. This is my new x2. Now I have to multiply a into x2. This is the iterative process. Now I have to take my a. I have to multiply with my new, this one. This is my new eigenvector. I have to multiply with this. Look at that, 25 into x2. This is my new eigenvector. Now take a and multiply x2, a into x2. Again, do the same multiplication row with the column wise. Do the multiplication. I will get this. Again, take the largest, numerically largest value as common. Then you will get this is x3 new. This is new eigenvector. Now multiply a into x3. So when I can stop the step? So it should converge the eigenvalue. You will get the repeated values here until you have to continue the iterative concept. Until you have to continue the iteration. Right. Now a into x3. A matrix and this is x3 matrix, multiply both. So this is the largest value. I have circled it. So that value you have to take as common 2.178 into a new value. This divided by 25.178. This divided by 25.178 you have to do. So this value will get. This is what my new x4. Multiply a with x4. So 25.178 I am having. Take AX4, A into X4, again 25.183. Previously 187, now it's 183. So we have to continue the process until it has to converge. If once the eigenvalue converges, automatically the repetition will get in the eigenvector also. Right. Now this is my new x5. Multiply A into x5, A value. Okay. Now take this is x5. This is A into x5. Multiply both. You will get this 25.182. Take that as common, 25.182 enter. This is the new eigenvector x6. Now a into x6 will be, this is x6. A into x6 is equivalent to this 25.182. Previous one also 25.182. Now we are getting the repetition. So previous also 25.182. Now also I'm getting 125.182. If you are repeating thereafter, you will get the same thing. That's why you no need to repeat now. So what you can do simply you can do, you can write this will be the final answer. Eigenvalue of the matrix A, dominant, numerically dominant, dominant eigenvalue of A is 25.182 and the corresponding eigenvector will be this. This is what you have to give the answer. Dominant eigenvalue of lambda 1 is 21.181. So here AX6 in the sixth iteration it's going to converge. Right. This is 7, I think so. Previously 5 and 6 we have completed. Look at that. I will show you. Yeah, 5, 6 already there. It should be 6 and 7. 6 and 7. It should be 6. Here it is 7. So in the sixth iteration, it's converging, right? So dominant eigenvalue is 25.181 and the corresponding eigenvector is 1, 0.045 and 0.069. That's it, guys. This is the way to find eigenvalues and eigenvectors. I will explain with one more example. Find the dominant eigenvalue of A. It's for 2 by 2. It's so simple. And as I told you already, now particularly they are given. If they're giving like that, particularly you have to take the eigenvector. If they didn't specify that, like the previous problem, what we discussed already, we can take our own. That won't be the issue here, right? So particularly they have mentioned, so we have to take our x1 is 0, 1. Now A is this x1, initial vector he has given. So 0, 1, right? Now A into x1, multiply that. Now we have taken 0, 1. So what is the multiplication? It will be 0 plus 2 here, 0 plus 4. Then what you will get for this? It will be 2, 4. Which value we have to take? Largest value, numerically largest. If it is a negative value, if it is here also, we have to take that one only. So take 4 as common. Then what will we get? 0.5, here it is 1. So this is my new eigenvector. Multiply A into x2 now. A into x2 is again 5.5 is the largest one, numerically largest one. Take that as common. This is my new eigenvector x3. So now A into x3 I have to do multiply A matrix A and x3 as a column vector, new column vector. Multiply both. I will get this. This is my x4 now. So 5.365, not repeating. So x4 I have to do again. 5.371, not repeating here. 5.371. This is my new eigenvector. Again, multiply the new eigenvector x5 with your A. A into x5 you have to find. A into x5. 5.372. Previously 371. Now it is 372. It's going to converge, I think so. Yeah. This is my new eigenvector is x6. Now multiply A into x6. So yeah, it's repeating. 5.372. That's it. So there is a repetition. We can stop our iteration process. The dominant eigenvalue of the given matrix is 5.372 and the eigenvector is this. Suppose if they are asking to find what is another eigenvalue, then you know the concept. Sum of the eigenvalue equivalent to trace of A. There is a property. Sum of the eigenvalue equivalent to trace of A or sum of the main diagonal elements. Sum of the main diagonal elements. Diagonal elements, some of the main diagonal elements. We can say like that also. So what is the main diagonal elements? 1 and 4. 1 plus 4 equivalent to 5. So lambda 1 plus lambda 2 equal to 5. We found one lambda eigenvalue lambda equal to 5.372. So then we have to find lambda 2. Lambda 2 equivalent to 5 minus lambda 1. So I can get minus 0.372. So my lambda 1 is this and the lambda 2 will be this. This is the way to find the eigenvalues and eigenvectors and the rest of the eigenvalue also. In the next video, we will discuss how to find the eigenvalue, dominant eigenvalue and the rest of two eigenvalues. I will give another example for 3 by 3. Okay. Okay guys, thank you. We will see in the next topic. Please subscribe it. Then only we can see the video immediately if I am uploading. Okay. Thank you. Thank you for watching.